Да. Ну, действительно. Как бы, а как так может быть?
У вас запланированная трансляция была?
Да. Ну что, готов?
Пока пишет запланировано, да.
Сейчас. Ну и...
О,
Пошло?
пошло, но факт 2.
Ну ладно.
Поэтому, видимо, надо...
Что-то изменить. Ну, я скажу, спрошу, что там не так. Ну, хорошо. Okay, so today we shall be talking about fixed point theorem. Burrell fixed point theorem. Yeah, so actually it is the rare case when the person, so Burrell, well, as you know, he's a very famous French mathematician, and he invented the so-called Burrell groups. And so it is a very rare case when a person writes down a text and uses the name which is due to his own name. Yeah, so and in the book, and Burrell was such an example that because in his book on algebraic groups, this notion of Burrell subgroups was so famous at that point. So he couldn't, I mean, even I do not know if he was modest or not, but even at that point, there was completely no reason to write down different name or to call them in different words. So he called them Burrell subgroups. So, and today we shall be talking about main reason for introducing Burrell subgroups, and this is Burrell fixed point theorem. But before we should speak about complete varieties. Yeah? So as for complete varieties, so this notion generalized compactness extends compactness, the notion of compactness in usual topology, the notion of compactness in usual topology. And it is quite important to understand that, so this is the usual Hausdorff topology, so that Hausdorff. Two algebraic varieties, yes, so two algebraic varieties. So, one should do the warning that some people just loses this just words about Hausdorff topology. I mean, when they're studying the matter, and then they start applying compactness to the open coverings, the risky open coverings, which are automatically more or less. The notion of having a possibility of choosing finite subcover is called quasi-compactness in algebraic geometry, and the analog, complete analog of the compactness in Hausdorff topology is precisely what I'm going to speak about. And the problem is that for the definition holds for is analog for more or less analogous for Hausdorff manifolds, but in algebraic geometry you simply cannot prove the equivalence to the compactness that we understand the compactness in usual topology as having finite subcover for open covering. So this is the follows as follows. So X, So let us recall the definition. X is called complete. If for any y, algebraic variety, x times y maps to y, has the projection to y has the following property. Of complete variety, yeah. So for any z closed subset on x times y, so closed subset in the product, the image P of z is closed. Yeah, so of course one should also just take into account, so remark that x is assumed to be separable here. So x is assumed to be, I shall recall what it is.
And this
To be,
sign is not like product topology, but
yeah, so the problem, so as we have discussed in the risky topology, yeah, so the product topology doesn't make sense, yeah, because it is, I mean, it has sense, but it has nothing to do with the risky topology if you want to induce it. So you, first of all, you cover x, y, just that blackboard doesn't work. Yeah, so you cover x times y, but as the union of charts, and you can, so ui is embedded in some closed subset I, Vj is embedded as a closed subset in, so they are open, of course, in x and y, but they are embedded in the closed, corresponding closed subsets, and as a closed subsets in some affine varieties. So this embeds u times Vj in A and I times AMI. Yeah. Here it Mj, so here it is a closed subset. So you can just define the topology saying that the intersection with any open covering of Z should be closed. Yeah?
and being closed subset is good for functions.
Yeah, so, and if you want to get functions here, you take functions here and restrict it.
And if it would be not closed,
Then, of course, you can restrict function, but it is not clear how to write it down. I mean, just. So, if x is assumed to be separable, so here x is assumed to be separable, so the diagonal, the embedding of the just diagonal is closed subset. Yeah? In x times x. So actually one can show that there is the notion of there is the so-called evaluative criterion of completeness and of separability and of completeness, and this criterion is more or less so it is formulated in the same setting, but here there is so here the statement is somehow the part that about uniqueness, and here the statement of being complete is existence of the map. So that's why these notions are related, and you always, when you're speaking about complete varieties, you always assume about the separability statement. I mean, almost always. I mean, except in some exotic cases. So the reason is that so for any closed subset in the product, then P of Z is closed. So the other remark that when usually some people are proving this on the course, so that for Hausdorff topology, this is equivalent to compactness. So this is equivalent to compactness. So, I mean, if you are in the case when all those notions of compactness coincide, like you have sequential compactness and some other things, and so more or less, so in good cases when these notions coincide, this is equivalent also. It is one of the possible ways to reformulate the compactness. So, but notice what is good about that, it is formulated purely in terms of morphisms. And so moreover, so let me do another remark. So just if you have f x and y is called closed morphism, if for any z closed subset in X, the image of Z is closed. So f of Z is closed. And also you can, there is a notion of the base change. So there is a notion of a base change. So you can write down x, y, and given a morphism y tilde to y, so you can take the corresponding square, just a fibered product. So just, or the base change. Yeah? Hmm? The separable we defined before when we talked about diagonal. Yeah, so and the x is so just x x is separable. So take x to be separable.
And if x is complete, then it is automatically separable.
No.
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 So
I mean this notion. So this is the extra assumption, but I mean, so this is extra assumption, but I want to use it all the time, so that's why just these are different notions, and one doesn't follow from the other, but talking about complete usually that doesn't make much sense if something is not separable. Delta.
Delta is should be a closed morphism, or the image should be closed?
No, well, this is the image should be closed, but it is being closed morphism for embedding it is equivalent of this is I mean for if you have just inclusion of the subset, checking that it is closed, it is more or less equivalent to say that the morphism is closed. So this is somehow the generalization of being a closed subset as well. So, and this we won't need, but mainly, but I want to explain this. Yeah, so you can pick up the following subset. So this is, so you have P1 and P2. So this is the set of points x, y in x times y tilde such that pi 1 of x is equal to pi 2 of y. Yeah.
This is not possible.
В смысле?
Pi 1
Yeah. This is, yeah. Yeah, so just let me. Okay. Yeah, so sorry for the mess.
Now we mess with 1 and 2. F2 is
Ah,
for x.
yeah, sure. Okay. So these are just the maps where the images, so the images of the store are the same. And this, yeah.
Why you wrote one of letters as x and others as y tilde?
Ну, потому что он в Y, но могу убрать, хотите.
Что там? Нет, как раз непонятно.
В смысле? Ну, в смысле Y здесь,
Вот эти
а X здесь.
x, y с тильдой равнозначны в этом новой конструкции.
Ну да.
Но она, ну ладно.
Нет, они, ну, конструкция
y с
симметричная.
тильдой можно было бы написать везде.
X1 и X2.
Хорошо.
Но морально это как бы, морально вы интересуетесь свойствами вот этого морфизма, и его меняете, то есть вы смотрите, как этот морфизм, ну как бы для чего это сделано, что вы хотите поменять вот этот морфизм, ну изменить его какие-то свойства и перейти от этого морфизма к этому. И спросить, ну какие свойства у этого морфизма наследуются при переходе к этому. Да? Поэтому я как бы их вот, пишу несимметрично. Ну а так, конечно, это симметричное понятие. Хорошо? So this is a closed subset. So this is exercise, but not very complicated. And closed subset in x times y, yeah, tilde. And so this is called base change, yeah, so that y tilde of y is called base change of f1. Yeah, so that it is changing. And notice that you have, if you want to speak about fibers, so fibers over y, so that, yeah, so let me just write down tilde here. Yeah, so fibers over y, just a fiber over y. So f1 inverse, and this let us call it f1 tilde. So f1 inverse of y is equal, is isomorphic to the fiber over y tilde, where...
There is only one f1 tilde for diagram of
Нет, ну вообще говоря, может быть много y tilde, которые попадают в y, да?
Я не совсем про это. Я про то, что f1 тильда однозначно строится по этому.
Ну да. Ну в смысле, что с... Ну как бы, потому что это по индуцированной проекции на x. So f1 tilde is, and this f2 tilde are just are induced by the projections on the corresponding factors. Yeah, so you have just you have a natural map. So that's why I was writing P1 and P2 here. Yeah, so just P2. So this is P2, and F1 tilde is just a restriction of P1 to the corresponding subset. Ну точно. And F2. So,
It's not seems true because F1 was an arbitrary map.
F2. So there is just yeah. So sorry. There is.
I don't understand what that actually means.
Не, ну в смысле, что ну как построить вот этот морфизм и вот этот?
Ну, вот, мы начали с F1, такого
Ну,
В смысле, F2 строится как проекция, да?
ну, F2, ну в смысле, что вот это замкнутое подмножество в x на y, и F2 это ограничение проекции на x. Да? F2 тильда это ограничение проекции P2.
Нет, я все-таки вот на то, что, например, мы можем сейчас...
Не, ну вообще может быть много,
С тильдами.
но это определение. Мы как бы вот в этой конструкции, да, рисуем такую диаграмму. Можно ее определять с помощью универсального свойства, если хотите, но...
То есть, ну окей, просто там универсальный свойство нужен порядок, потому что можно перевести один стиль, какой-нибудь там элемент, какой-то другой по образу.
Не, ну да, давайте я договорю вот здесь. This it has the property that the fiber over y tilde where such that f2 of y tilde is equal to y. Yeah, so you have the isomorphisms of the fiber. And also you can just define it via universal property. So this this is as follows. So suppose you have x and y. Yeah, so you have this picture, and you have put it. So x. So you put this fiber product here. So you want to consider the following problem. So suppose you have a map from Z, yeah, so that the pair of maps, so P2 tilde and P1 tilde and P2 tilde. Yeah, so I have, yeah. So the projection to X is P2 tilde and projection to, y, and the map to Y is P1 tilde. So such that the composition of, so this diagram is commutative, yes? So the composition of P1 and F1 is equal to composition of P2 and F2, P2 tilde and F2. So if you have such commutative diagram that, so here you have, there exists this map to this fiber product, exists and unique. Okay? So, and...
Some kind of fiber product now.
а?
Did you define some kind of fiber product now?
Не понял. Ну вот,
Ну вот вы говорите сейчас про расслойное произведение,
да.
да? И
Ну, определение вот такое, вот она конструкция, а вот это можно, ну, его также определять с помощью универсального свойства, да? То есть как бы, что универсальное свойство — это такой объект, что существует, если z удовлетворяет этому свойству, то существует единственная стрелка сюда. Yeah, so this is just to mention, and also I wanted to say that there is a notion of proper morphism. So just x is called proper if it is universally closed. So this is closed under base change. So closed. So any base change is closed. Yeah. So any base change. So this F tilde is closed morphism. So the morphism from X, Y tilde to Y tilde, yeah, is closed morphism. And so this is the most general definition that can be found in Hertzhorn book. And the connections between this one and this one, so usually when you're speaking about varieties, so the variety can be considered as the morphism to the point. So you see that remark that you have the full X is complete as the variety if the map of AX to the point is proper. The morphism is proper. And the reason for this is that when you are making a base change over the point, so base change over the point is just a product. Over closed point is a product.
You mean not base change, but what base change is a morphism?
I mean the following. So if you have X maps to to the point and Y maps to a point, yeah. So the base change of this map to the point is just X times Y, the morphism of X times Y to Y. So this morphism is precisely what you see here. Yeah? Okay. I just let me write it down somewhere. Just like here maybe. Yeah, so if you make a base change, so you can do the following. So you can take X, take a map to the point. And if you take this Y, yeah, so this variety Y, it also has the map to the point, to the same point. I mean, at least when you're working over the field, so it is clear that you have the maps from Y to the point. And then you can take the fiber product. So if you apply the construction of fiber product, so these maps to the points are unconditional. So you have just as a direct product of varieties. So the base change of F, thinking of as the map of X to the point, is just the projection from X times Y to Y. So if you apply this this definition to the map from X to the point, you shall have precisely the statement that for any Y, this morphism should be closed. So the image of the closed subset here is here. Okay?
So completeness is more general than properness.
The properness is more general than completeness of the variety. The properness of the morphism is more general as completeness of the variety. But in a sense, so this is called relative situation usually, and this is called absolute. Yes. So, okay. So let me. This is just to put everything together that you could study in more advanced courses on algebraic geometry. But I want to discuss some properties why the complete varieties are important. So properties of complete varieties. So properties. Complete. So the first one is that the closed subset of complete variety is also X is a closed subset. X is complete. Then just W is complete. Yeah. So this just follows from the following, that you have to consider this morphism. Yeah, so for X, in order to check that X is complete, and in order to check that W is complete, you have to consider this morphism. So here, if you take Z inside this product, it is clear that Z is closed here. So closed here in the product. So you get that the image under this projection is also closed. Yeah? By the above, because it is already closed upstairs. So the second important property, that if you have X, Y, and X is complete, and Y is separable, then for any morphism, F algebraic morphism, then if you just have, so notice that if you have if X and Y were topological space, so then the F was continuous map, yeah? So the image of compact is compact. Yeah? So here there is an analog of the statement. So if you have just X is complete, Y is separable, this is some technical assumption. So F of X is closed. And notice that if Y was Hausdorff, then the image of the compact is closed. Yeah? So then you know that F of X is complete variety and closed in Y. So the third property I want to discuss is the following. So that what is the difference? So what character more? Yeah. So So this is the question that do we have sufficiently many examples of complete varieties? Yeah. So and the answer is yes. So Pn is a complete variety. So this is so this is not very easy statement. And since the closed subset of complete is complete, then any closed subset in Pn is also complete.
It's what we call projective variety.
Yes, so what we call projective variety. So it is complete. So actually, this is the reason why we like to study projective varieties. Actually, for one of the reasons we like to study them is for completeness. So of the closed subsets. And now what we shall use today to prove a fixed point theorem. Yeah, so this is the following. So if just k of x, so x is complete, x is complete, and so you may ask about the set of regular functions, yeah? And the set of regular functions on x is just trivial, so it is just constants.
Это четвертое свойство, да.
Да.
Просто в это не написать.
Поймали. Yeah, so and the reason for this is very funny, so let me prove it. What is the function? Yeah, so the function is just a map. So f is a function, regular function. You can think of regular function as a regular morphism to A1. Yeah? So regular map defined by the function. And if you have this regular map, then, of course, you can do the following. So you can take the composition. Yeah?
Maybe x is complete
Complete, reducible.
irreducible.
Yes, of course. Otherwise, yes. So if you have the map from x to A1, you can embed the A1 to the corresponding P1. Yeah? So this gives you also some map, yeah? So f tilde. And notice that f is complete, so you apply the second. So by the second, f of x is closed subset in A1. And what are the options? Yeah, so the options for closed subsets of A1, so this is f of x is a finite set of points.
Which is impossible due to irreducibility.
One is possible, yeah? 1 point is possible. Subset of points. And this, of course, if this is the case, then x is irreducible, so this is 1 point. Yeah, so this is 1 point. And this implies precisely that the function is constant. Yeah? So f is equal to some constant, precisely at this point. And if the function is not constant, then it should be a closed subset of A1, so this is full A1. But notice that full A1 is not possible because image of composite, so assume that f of x is A1, so this is not possible in our case. So since if you have f of x is A1, so the f tilde of x will be A1 in Pn. And it's not closed, yeah?
Can we just say that A1 is not complete?
Ну а как это понять? Вот мы это так понимаем.
Есть произведение двух
Не, ну как бы, ну,
Это проще.
не, ну вы попробуйте проверить, а потом...
Что сказали теперь?
Ну в смысле как контрпример? Ну да, да. Да. So which is so which is not closed in Pn? In P1, yeah, so that you have a contradiction. Yeah, and of course, yeah, so the hyperbola gives you the example. Yeah, so I should have precisely give you the example of where this doesn't hold, so for variety which is not complete and this projection is not closed. So. Yeah, so this is precisely the example mentioned, that this hyperbola is a closed subset. And its image is A1 without 0, yeah, so pi of z. So this is closed in A1 times A1. And you have a natural projection to A1. So pi of z is just is isomorphic to A1 without 0, so this is not closed. So A1 is not closed, not complete. And so the thing is that, yeah, so just to use this completeness, you have to use both statements, and they are actually proved. And if in order to, so we need here is only that the image is closed, not that the image is complete. So I mean, just you need only part of the statements in this setting, if you write down the proof this way. So yeah, so what is the reason of talking about 4, despite the fact that invariants, that the functions are regular functions are important invariant of algebraic variety? That and characterize algebraic variety. This tells you that affine varieties. So if you have just x is irreducible for simplicity, affine and complete, then it is just a point. Yeah? And the reason is the following. So for affine varieties, so if x is affine, if so then the algebra, its algebra is equal to k if x is a point. And the reason is that if you have more than 2 points on x, there is always a function that have different values. Yes, so if you have x and y on x affine varieties, then there exists f in k of x such that f of x is equal to 0 and the f of y is not equal to 0. Okay? So this is non-trivial function. And the one can find such function just as a linear function, yeah, so that x is put in the affine space, and you just take the linear function containing x and y is hyperplane and not containing y. Yeah. So this shows that, and for complete varieties you have the property that this is a point, so that you get that this can happen only if x is a point. So now we can pass to Burrell fixed point theorem. Yeah? So just I wanted to write down if y equal to 1, but then I decided to write if y is not equal to 0, but then I failed. So Burrell fixed point theorem. So this. Any questions? Да по-русски спросить. Да. 5. А? Да.
Ну, одно это, что замкнутый под множество полный тоже.
Да. Что?
А дальше я усну.
Ну, второе свойство, которое стер, это второе свойство, это если у вас есть x, морфизм. Но вот это нам понадобится, что есть морфизм из x в y, то образ x отделимая, то образ f от x тоже полная и замкнутая. То есть это аналог, что образ компакта компакт. Ну, еще было свойство, что алгебра функций на полном многообразии.
А вот у вас написано сверху.
Да, нужное свойство. Алгебра функций на полном многообразии просто, просто является константами. Да? Да, на полном неприводимом. Но иначе это просто сумма k. Сумма.
Неочевидно это то, что Pn полная.
Да, и там был очень факт такой, что Pn полная. Нет, вот то, что образ замкнут, он тоже не совсем очевидно. Там надо графиком воспользоваться. Можем это понять. So how to write down? So the trick is that in order, let us explain that the image of complete is complete. So the reason is the following. So if you have what we have so far, we have the property that the image of the projection is complete. So if you take a closed subset here, so then the projection of this closed subset in Y is also closed. So the idea is just if you want to prove that this is complete, you have to realize it as the closed subvariety here. Yeah, so just as the image of the closed subvariety. But here you have a natural, so for f, the map from x into y. Yeah, so you have the graph. Yeah, so you have the graph, which is just the x and the f of x. Yeah, so for the pairs of points in x times y. The only thing, so if you show that it is closed, so you see that the f of x is just the image of the graph. Yeah, so that this is pi of y. So just f of x is just pi of y of gamma f, and this is closed since x is proper. Yeah?
Morphism can be proper.
Чего?
You give definition for proper morphism.
Нет, ну тут именно нет. Тут вообще для любого. Если x уже замкнутое, то образ... Если x полное, то образ его всегда полный.
So since f is proper, or since
Нет, x is proper.
complete.
X is complete. I mean, sometimes I use the same word for the reason because the morphism to the point is proper. Yeah, so, yeah. So, and the graph is closed due to the following. So you have to realize a graph as, yeah, so the idea is that you can realize the graph as follows. So you have a natural map here, yeah, so that maps x and y to f of x and y. And if you take a diagonal here in y, so the just the preimage of the diagonal will be just the graph here. Yeah, so that's why I was assuming that y is separable. Yeah, so to guarantee that this is closed, since y is separable. So this realizes the graph as preimage of diagonal, and this is very easy. Yes, so you have to take so the condition of so there are two conditions. Yes, so just you are saying that f of x. So if you are considering the points from the diagonal, you are considering f of x should be equal to y. So which is precisely the graph. Yes, so the condition of having the graph. So the graph is realized as a preimage of diagonal. It is closed, and the image is closed. Вот это, Burrell, no. It is just moving from the blackboard to the blackboard. Okay. So, okay. So why not to mention good name many times? Yeah, so, okay, so let us have the following thing. So suppose G acts, so G is a solvable group. Fine, yes. Acting on complete variety X. So I'm formulating this a little bit more tricky as since we're just this what I shall formulate holds for algebraically non-closed field. So then the set of fixed points, then the variety is just the variety of fixed points of fixed points is not empty. So, so what is just I denote it as xg. Yeah, so what is just why I'm formulating this in so quotient way. So just let us do the warning. Yeah, so if K is not algebraically closed, it can happen that X is non-trivial, but the set of fixed points, the set of points is empty. Be non-trivial, but xk is the set of k points. I mean, you can think here as follows, so that just the k points can be thought as the image of, so the point itself is just the affine variety with the algebra of functions equal to k. So you can think of xk as the algebraic maps from k to x, which are defined over k. Or in naively, you can cover x by the charts where the charts are defined over k, so that the inclusion of the charts are defined over k. So these are affine, so meaning the following. So these are closed affine, so these charts are, so they are embedded in ki in a way that they should be defined by some system of equations. Yes, so this system of equations is just defined. So the set of algebra functions on k of y is just the polynomial algebra.
What is the map of k to x?
Не, ну я как бы ладно, это мы не будем говорить. Давайте обсудим, что такое быть определенным над k. Ну вот, не, ну как бы я хочу сказать следующее. Для афинного многообразия это понятно, да? То есть, ну как бы вот если x вложено, so if x is embedded as a n as a closed subvariety, then
an is corresponding to k bar.
an is just a affine space. I mean, the coordinate space. Over some field. So it is just the product of a1 over k, where a1 is defined over k. So the algebra functions here is just k of x, yeah? In some power n. Yeah? So the algebra functions here is just a polynomial algebra of n variables. Yeah? So this is being, so this means that this variety is defined over k. So then you can speak about k points. So k points, of course, so here points are coordinates. So key points are just coordinates with values in key. Yeah?
What are key points? What are they?
Ну, сейчас, извините. Ну, в смысле, x вложено в афинное пространство, у афинного пространства есть координаты. Но вот мы называем k точкой, просто если ее координаты, это просто ну, числа из k.
По-моему, тут должно быть k-бар вот, у второго.
Нет, ну в смысле... Нет, ну как бы тут можно как угодно, ну то есть как бы x можно реализовать, ну как бы как хотите, можно...
Иначе просто всегда координаты
Ну,
будут, что бы мы ни сделали.
нет, ну как бы, ну дайте, да, вложим в k с чертой, но вот мы говорим при таком вложении, ну, k точках, что, ну, да, что просто, да, у части точек будут координаты в k с чертой, вот у данной точки x, у нее координаты из k.
Ну вот, я никогда не понимал в этом мнении, как все очень завязано на конкретные карты.
Ну, как бы утверждается, что это, если вы, ну, как бы, нет, ну, конечно, над k с чертой, ну, в смысле, вот этот, тут вопрос такой, ну, как бы, как задано x? So the main question, how we define x? So we can define x as the collection of polynomials. X can be defined as key variety. So the k variety means that it is defined by equations with coefficients in k. By equations with coefficients in k. So when you're speaking about such varieties, so you can speak about morphisms of such varieties. So morphisms of such varieties are morphisms such that they are given in terms of functions, so that they are restrictions of the regular functions over k. So you can also speak about the regular functions over k. Yeah? So if you introduce the morphisms between k varieties, so meaning that x, so here x you embedded in some an, y is embedded in some am. Yeah, so you can speak about that the pullback of regular functions, which are restrictions of these functions, is also the regular functions here. Or you may say that you have inclusions in affine space, and the map between affine spaces is given by the polynomial with coordinates in k, so over the given field. Okay? So that's why you can speak about key morphisms. Да. Это имеется в виду, нет, имеется в виду следующее, что как множество, оно не пусто. Ну, то есть, как бы может так быть, что x это нетривиальное подмногообразие над полем, ну, то есть задано уравнениями, но множество это не пустое множество, как множество, заданное уравнениями, но множество точек на нем пусто. Но, ну, как бы... Ну, то есть, ну, например, вот как бы типичный пример, который это дает, это что сумма квадратов, ну, над r, да, сумма квадратов равна минус единице. Давайте я приведу пример, чтобы было понятно. Вот как такое может быть, что, ну, so the example of over R, so the following object in AN. Yeah? So you can consider the sum of squares is equal to -1. Yeah, so of course this equation doesn't have the solution. But the set of points So it doesn't have solutions over R, but it has solutions over C. So as the set of the set of points of this solution is empty, but as the set which is defined by the polynomial equations, it is not empty.
Because we can apply these polynomials to C. So we can
Yes, we can extend these polynomials to C, and this this gives you this gives you a non-trivial point. Or another way, so you are saying that the affine variety is empty if and only if its algebra function is trivial. Yes, so if x is affine, so since x is characterized by the algebra of regular functions, so you can consider k of x to be the polynomial algebra. So here in this case, so you consider the polynomial algebra modulo this relation, yeah? Just the sum of xi square minus 1. And this is, I mean, if x is plus 1, yeah. So if x is, x will be empty if and only if this quotient, I mean, if this will generate the whole polynomial ring, so the quotient will be 0. Yeah? So just x is empty if and only if the quotient k of x is equal to 0. But for this particular equation, this quotient is not 0.
It's definition of empty set.
Но оно не пусто, понимаете? То есть это множество, ну то есть вот этот полином, он определяет пустое множество точек, но не пустое подмногообразие.
Пустое многообразие?
Не пустое многообразие. Потому что ну, пустое многообразие, это то, афинное многообразие, это то, когда алгебра функций тривиальна.
Может, не тривиальная алгебра функции, если есть функция реальная функция, то она множество пустое.
Нет, функции только надо увеличить.
Вы просто точки, вы не можете, вы не знаете значение этой функции в точках вашего многообразия. Но множество функций есть. Но, да.
Вопрос. А вот правильно, что x же не пусто, тогда это тогда, когда k с волной точки?
Да, но как бы это правда. То есть, so there is a statement that x is not empty over k. So if x is defined over k, then x is not empty if and only if x of over k bar is not empty. Yeah? But x of k bar is not over k bar is non-empty if and only if the set of points of k bar points is not empty. Yeah, so
X defined over k bar.
you just consider the solutions of the system of polynomials over k bar.
So X
So just xk bar has non-trivial points. This is actually exactly the statement of one of the statements of Hilbert Nullstellensatz. Хорошо?
So now we can adopt the algebraic but x of k equals set of k points.
Ну, не, ну как бы тут нужно отличать следующее. Ну как бы вот подмногообразие — это не его множество точек. Подмногообразие — это объект заданной системы уравнений. А вот как бы на нем можно рассмотреть множество точек. То то есть множество точек над каким-либо полем. Да? И вот, ну, можно его рассматривать, да, над R, можно над C, можно над, ну, любым другим полем, если можете, то можно, ну, как бы, то можно это рассматривать. И как бы, ну, если у вас алгебраически замкнутое поле, то непустота эквивалентна тому, что на нем есть точки.
Но не пустота — это свойство уравнения.
Ну да, но не пустота многообразия — это свойство уравнений. Но его можно переформулировать через наличие точки. То есть если система уравнений не пуста, то над алгебраически замкнутым полем всегда есть решение.
А характеристика поля у нас, например, зафиксирована.
Но это не важно, ну просто над любым
Вот,
полем.
например, уравнение, там, я не знаю, x плюс x равно.
Ну, в смысле x плюс x? Нет, ну нетривиальное уравнение должно быть. Нетривиальный элемент, ну, нетривиальный полином хотя бы, да? Ну, в смысле?
2x равно 1. Это нетривиальный полином.
Ну, где? Ну, в характеристике отлично от двойки. Полином — это не запись. Полином — это нетривиальный элемент k от x1, xn. Ну, вот это алгебра функций. Ну, как бы, если у вас, ну как там, у вас нет элемента 2 в поле характеристики 2. Извините, но его просто нету. Поэтому это не полином над полем.
Можно там x квадрат плюс x равно 1.
Но это будет уже нетривиальный полином, он будет задавать нетривиальное подмножество. Хотя он может быть там тождественный, ну, как бы. То есть он может, ну, в этом-то как бы дело, он может не разделяться, ну, не определяться своими значениями, но это будет как бы все равно нетривиальный полином. То, что он задает, будет нетривиальным под многообразием.
Но вот там, где x от k это сету, key points, это что?
Ну, вот это следующее, что, ну, как бы, если у вас x вложено в афинное пространство, то понятно, что такое k-точки. Да? Если у вас есть морфизм между многообразиями, мы определяем морфизм над k. Ну, это то, что как бы у вас x и y вложены как k многообразия, то есть заданы уравнениями с коэффициентами в k. И вот здесь вот это отображение тоже уравнение с коэффициентами в k. Так? So the just polynomials given by polynomials with coefficients in k. And if you are speaking about variety, how you define it? Yeah? So you define it by gluing charts. Yeah? So these charts should be... Ну, вообще, вам как бы объясняю, вы в телефон тупите. Но, у вас больше всего вопросов. Yeah, so you have UI, which are charts, so they have the corresponding inclusions in Ni, so these inclusions are defined by polynomials over k. So defined by, so equations are defined over k, so by polynomials over k in k of x1, xn. And then, in order to glue the variety, you have to construct the mappings between charts, the isomorphisms. So you are considering the isomorphism is ui, where you intersected with j, and you should have the regular map to uj, where you restricted to ui. So these maps should be also defined over k. So defined as the varieties. So we defined what is variety defined over k, and this tells you that the set of k points are precisely the following. You take these charts, take these embeddings, and look at those points that have coordinates in k. And satisfy the...
K is such that all the coordinates are lying in
Yes, yes,
closure.
yes.
It's not arbitrary coefficient, arbitrary coordinates, but coordinates in good structure.
Yeah, so the thing is that you should have the structure, so this embedding should be of special kind. I mean, so your I is not arbitrary embedding, so it should be defined by the polynomial with coefficients in k and not in k bar, in order to have well-defined notion. Да.
Вот, например, иначе у нас было бы там c как многообразие над r, вот у него было бы, там, я не знаю, точка 1, это была бы r точка, а точка 1 плюс i не была бы r точкой.
Ну да, так и есть. Ну, как бы c только, но это a1, да? Ну, то есть вы можете смотреть у него, ну, c, думать о c как о c точках, то есть это все c. А можете думать как об r точках, это r. Ну.
Теперь, типа, когда мы думаем как о c, то там все равно внутри вложен r точка.
Да, ну, как бы.
Они вложены именно как 1, 2, 3, а не как там 1 плюс i, 2 плюс i, 3 плюс i,
Да, но у c, но вообще у многообразия могут быть разные вложения над r, разные структуры. То есть, ну, например, как бы можно вложить, ну, вот, как бы вот эту вот штуку, да, ну, над, это квадрика, да, то есть, ну, как бы над, ну, то есть вот над x1, ну, если мы напишем, so if we write x1, x square is equal to minus 1, yeah? So this is isomorphic to quadratic. And this is, I mean, if you consider the projective space, so this will be the quadratic without points. Yeah? So on P2 without points. Over R. Because if x3 is non-trivial, you can divide by x3. If x3 is trivial, you have the sum of squares equal to 0. This implies that both of them are 0. So this means that all coordinates are 0. So this is not a point of P2. And this gives you, and notice that this quadratic is in gradients of course, you have proved that it is just isomorphic to P1. Yeah, so if you have a point, you can project this quadratic to P1, and this projection will be isomorphism over the field where this point is defined. And for example, over R, there is no points on quadratic, so you cannot project from the point, so you cannot identify the quadratics without points with P1 over R. So this gives you example of the variety which is isomorphic to P1, but over C, but not over R. Yeah? So, and the reason that they are not isomorphic because this has points over R and this doesn't have points over R. Okay? So the trick is that the variety X can be non-trivial, but the set of points can be empty. So the Burrell fixed point theorem doesn't give you the real fixed point. I mean, it gives you the existence of the fixed set. So just additionally, so over k bar, since so you have the following remark. So since if k is equal to algebraic closure, the x is not empty. If the set of fixed points, the set of k points is not empty, then if Burrell theorem implies that there exists x in the set of the k points. So a fixed point.
So invariance of fixed points is not the same as the set of fixed points.
Yes, yes. The,
What is the difference?
ну, многообразие неподвижных точек — это множество, ну, поскольку мы говорим, да, это идеал. Ну, тут как бы нельзя говорить об идеале в конце функции, потому что x, она проективна. Но это, ну, то, да, но это то, что склеено из афинных, а вот эти афинные, они нетривиальные идеалы в кольце функций, ну, которые определены над k, над полем k маленькое. И вот как бы причина такая, что сама теорема Бурреля говорит, что это множество не тривиальное, но при этом, ну, как бы она не говорит, что на нем есть точки. То есть, как бы, ну, Да, что многообразие нетривиальное, но как бы оно не говорит, что на нем есть точки. Ну, вот как бы это, поэтому теорему Ли вот как бы формулирует, ну, то есть теорему Ли формально мы можем вывести только над алгебраически замкнутым полем. Да, которую мы в прошлый раз отдельно доказали, но просто так. В общем, как бы она из этой теоремы следует, но над алгебраически замкнутым полем, а в той формулировке, как мы сказали, она неверна. So the theorem, the Lee-Colchan theorem that so let us recall that we have proved the Lee-Colchan theorem. So that was stated as follows. So G was solvable group. Irreducible, sorry, otherwise. Just reducible. Acting on the vector space, so you have G maps to GLV. Then, if k, so over k equal to k bar, so then it has a fixed point. Yeah, so it has a fixed point in the projectivization. So we had so it is the particular case of the theorem of Burrell. And the problem that we have formulated the Lee-Colchan theorem in terms of invariant, semi-invariant vectors. Yeah, so, in Lee-Colchan theorem, we have precisely stated that we need a semi-invariant vector, so which is precisely the fixed points. Of course, so it is not so convenient to formulate this theorem just in the setting of algebraic variety. But when you're already in this setting, then it is much more convenient to state it like this and to prove it in more general contexts. And of course, yeah, so we used that, here we used that P of V is complete. Yeah? Okay. Ну что, давайте перерывчик сделаем.
Потом докажем, что делать.
Да. Мгм.